Oh, okay. You hear me? Can you hear me? Can you hear me? Okay. Can you try now? Can you hear me? Okay, great. So let's get started. So we have, let me see who's checked in. We have Van, Abdullah, Agandi, Ibrahim, William, Manny, Rawa, Muhammad, Alkaldi, Aaron, Douglas, and Christian. Is Jesse here? Or JC here? Okay, is my voice clear now? I need to get closer to the microphone. Okay, all right. So what we have today is we're going to continue the example that we put together on last last Thursday. Okay. So before we go into detail how to simulate these circuits, let's make some announcements. The first one is there's a tutor available for this class, remote tutor. So if you go to ULearn, if you look at the announcement on ULearn, I give you the detail how to sign up for tutor. So if you go to ULearn, you can see that there's a number you need to call, and you can make an appointment. Then they're going to remotely help you, probably Skype or Zoom or whatever they want to use to help you on the subject for this class. Okay. So any question about the tutor? No question? And I assume it is all set. All right. So next announcement is probably you receive an email regarding pass or fail option for classes during this term. Okay, please go through the email in detail. If you need to sign up for the pass fail option, please go ahead. They give you the instructions. Okay. We do not handle it here by the instructor. The student academic services take care of that. But you need to go through the channel properly to get this thing done. Okay. All right. All right. Next is about the project. So if you go to ULearn, I gave you a video. I gave you a video about the baseline for the project. Okay. Have you watched the video? Yes, Muhammad. Yes, I saw you. Yes. The project baseline. There's a video about a program running on Neos 2 on the DE10 Lite. So have you watched the video? If you have any questions, if you have not, please go ahead and watch it. Very short video to show you how the program is supposed to behave. Okay. So for those who have already watched the video, any questions? Okay, can you hear me now? Very interesting. The voice is active on my side, but I don't know why. Sometimes you don't hear me. Okay, I think it's just the microphone position. So right now, I think it's better now. Okay, so my question was, have you watched the video about the project baseline? That's what we're going to use to create a project. Okay, okay, that's good. So that one, if you have that program done, please just keep it that way. We're going to use that as a baseline. If you have not, please get it done by week 6. Okay, it's a fairly straightforward program where you just need to randomly generate some numbers and then just match the patterns horizontally, vertically, diagonally left to right, or diagonally right to left. Okay, all right, so let's continue. All right, so let's get back to the subject for today. Okay, this is assignment number D2. Any question on D2? Any question on D2? Okay, I take that as no question. That's good. Okay, so let's look at the code that we generated just last week. If you look at the code, this is what we did last Thursday. Okay. Now, one thing that you can do is you can maximize the screen. There's a button here. When you click on it, it's going to detach the window and then make it its own window so that you can see more code. Okay. Okay. If you have a problem with the JTAG for your hardware, very easy. Usually it's the USB cable because we're using the same virtual machine. Your USB cable probably is bent. Remember, these are USB cable. You cannot snap the cable very hard. You know, make sure that the cable is short, the cable is straight, the cable doesn't make any sharp turns. Okay. Okay. Oh, today is March 31st. Okay, good. Thank you. All right. So this is the code from last week. Basically, all we did was we uh, have two inputs, key 0, which is our reset active low, and we have a clock that's available to the DC10 light, sorry, DE10 light, okay? And what we did was we designed a counter that will increment by 1 every time there's a clock, and then we connect we connect the counter to the output Q. Okay, now you don't have to connect to the output. The counter can be internal, but just for this example, we connect the counter to the output. Understand? Okay. Next, what we're going to do is we're going to compile the project. So processing, start, compilation. Okay. Yeah, if your USB blaster have a yellow triangle, that means the driver is not there. You need to reinstall the driver. Yeah, the USB blaster driver it's corrupted. That's what happened. Yeah. Then I need to look at it myself. I cannot debug it for you right now because I don't have the hardware. Usually it's the driver. Yeah. If it is consistently giving you 61% fail, very easy. You just download Day1, which you turned in last week. Okay? If it doesn't download, then something is wrong with the hardware. Or you can easily just change the USB cable and try again. Because I've seen the USB cable broken over time. And these cables are very standard. You can get it from any store, or probably even from your cell phone or your printer. Then you can use that cable. Okay? Okay, so after compiling the project, you should see no error with some warnings. Okay? No error, some warning. That's fine. The next step, we're going to simulate this. So to simulate this, the same routine, tools, run simulation tool, gate level simulation. Okay, so these are the typical window. You have the library, object, processes, and wave. Okay, all right. So let's start the simulation. Simulate, start simulation, and select the circuit. Design 0. Resolution is 1 nanosecond. Click OK. Then you have the waveform window, you have the object, and you have the library, so the simulation. Okay. Okay, JC, are you here? I don't see you checking in. Okay. All right. So we're going to put together the commands for the simulation. So by now, everybody seems to know how to type in the commands. So the first thing you do is you need to put the waveform. So you need to put the inputs and outputs on the waveform window. Okay. So do that. So in this case, I'm going to change my colors. Okay. So we'll always use green for the outputs and blue for the inputs. So now I'm going to try different colors. Okay. So I'm going to type this in. Well, you give you error because you didn't type in the code the way it's supposed to be. So look at your code. Which line do you have error? So I'm going to add the input key 0 using magenta for my color, blue for the clock, and green for the output. Okay. So let's do that. So now I have the color. Okay. So if you don't know the commands, here are the commands we need to type in. 3 of them, one for each input. Okay. All right. Are we good? Can we move on? Okay. So the next command's a little bit tricky. Now, if you have a circuit where there's no clock, you can just start activating your inputs and then go through the truth table. But when you have a clock and a reset, you have to be very careful. The reason is when you are in reset, the clock doesn't really matter. You know, okay, you can always have the clock. If the circuit is in reset, the clock doesn't really matter in this case. So for our circuits, since we have an asynchronous reset, okay, remember our reset is asynchronous. Okay, so the clock does not matter, and the clock always runs. Okay, the clock always runs. What it means is the clock will run forever. So it goes from 0 to 1, 0 to 1, 0 to 1, 0 to 1 at a particular frequency. So the challenge here is if you keep typing in 0, 1, 0, 1, 0, 1 forever, it's not going to be efficient. Your command will be super, super long. So in Modelsim, they give you an option. If you have any clock input, you can use this command, where you type in one command and it is going to repeat the clock forever for you. Okay? So today we're going to introduce this command. Okay. So the next two commands is to force the reset or to activate the reset first. Okay. And then the circuit's supposed to respond to the reset. So these are the two inputs. So two commands. So the first one is to force the key 0 to 0. That means you want to activate the reset, and then you want to force the clock to be 0. Okay. So please make sure that type this in now. Two commands here. Okay. So I'm going to do that, and Now the reset is activated, and the clock is deactivated. Okay, now you can see my screen, right? I was switching between windows. Okay, so once you put in this, you need to run the simulation for a certain period of time. So in this case, we're going to run it for 40 nanoseconds. Okay, then we'll go over why we want to run it for 40 nanoseconds. Okay, all right, so run 40 nanoseconds. All right, so when we run 40 nanoseconds, you see this is happening. Okay, now if you zoom in enough, you should see that output Q is 000. So that means this is a 3-bit value, because by default everything is binary. So this is a 3-bit output. Okay. Now why do we run 40 nanoseconds? Okay. It has to do with the clock speed. Okay. Now if you look at our circuits, we have a synchronous reset key 0, and also we have a clock. So if you go to the menu of the board, scroll, look at the clock. It says there are 3 clocks available on D10 light. Okay. These 3 clocks, 10 megahertz, 50 megahertz, and 50. Okay, now we're using max 10 clock 1 underscore 50. And it is 50 megahertz. Okay, so for 50 megahertz, the clock period is equal to 20 nanoseconds. So when you look at Modelsim simulation, you want to deactivate the clock, you need to deactivate it for a couple clock cycles. You don't want to just do it for one. So you do 1 clock cycle, 2 clock cycle, so it's 20 nanosecond plus 20 nanosecond. You can do it for 200 if you want, but you don't need to do that many cycles. Usually it's minimum 2 cycles. Okay, that's why we use 20 plus 20, which is 40 nanoseconds. Okay, do you understand why we run 40 nanoseconds now? Okay, so let's continue. So right now, the simulation has already advanced in time to 40 nanoseconds. That's why you see these waveforms. Okay. So next, we're going to activate the clock, but deactivate the reset. Because if you keep activating the reset, nothing will happen. Okay. So to do that, we're going to use this command. So look at this command. We put we put the key 0 and 1 after 20 nanoseconds. Okay, so starting from now, key 0 will be 0, then 20 nanoseconds later is going to be 1. Okay, okay. And the next command is this. So this command is what is after the dash R is the period of your clock. In this case, is 1 over 50 megahertz, which is 20 nanoseconds. By the way, it's Corbin here today. Is Corbin here today? Yes, the streaming is lagging. I think right now too many people are using YouTube. That's why the speed is not that great. All right, going back to our program. All right. So what is after dash R is the period of your clock. Okay, and what is before this is when you see a falling edge. Okay, so by default it's supposed to be 10 because it's half the clock cycle. Okay, and this is when do you see a rising edge. Okay, usually it's 0. Okay? So this means I'm going to see a rising edge, then a falling edge, then a rising edge. Okay, however, if you want to put some delay in the clock, this and this number will change. Suppose suppose I want to put a 5 nanosecond delay. I put a 5 nanosecond. That means my clock won't start until 5 nanoseconds. That means this also increase by 5 nanoseconds. Okay, so both of them will be delayed by 5 nanoseconds. That's why it is 5 and 15, because it's 5 plus 0, then 5 plus 15. Okay, so if you do this two commands, these two commands, and you're going to run your simulations for many clocks. So in this case, we want to run it for more than one clock. Okay, so for example, we're going to run it for 100 nanoseconds, which is 5 clock cycles. Okay, all right. Yeah, Christian, I got you. No, I don't. Is JC here? No. So if you look at the screen, the simulations resume and continue from where we stopped. Remember, the first set of commands, we stopped at 40 nanoseconds. So right now, it's going to pick up from 40 and continue. All right. If you want to go back in time, you must restart your simulation. You cannot say, all right, let's go back negative 20 nanoseconds. Sorry, you cannot do that. You can either go all the way back or continue from where you left the simulations. Okay. Thank you, Manny, for the feedback. Yeah. Okay, hopefully he's doing fine. All right, so now if you zoom in to the waveform, you can see that the value for the output is changing from 0 to 1 to 2 to 3 to 4. So these are the binary combination of 0, 1, 2, 3, 4. And interestingly, look at the first clock cycle. Nothing happened. Why? Because the reset is still activated, which is 0. That's why whether you have a clock or no clock, the output will not change. This is a property of asynchronous reset. Asynchronous reset outputs is not depending on the clock. Okay? So now you exercise a circuit with 4 clocks, so output changes. You can run another 100 nanoseconds. Then the circuit will activate more count. So if you look at it, let's zoom out a little bit. You can see that the count is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and then repeat. So from 1, 1, 1 to 0, 0, 0, because you roll over from 1, 1, 1 to 0, 0, because you only have 3 bits. So after 1, 1, the next bit is going to be 0, 0, 0. And then you continue. And this thing will go on and on and on and forever. Okay, so for 8 combinations or 3 bits, you're going through all this. So this is a binary up counter. So what we just built today, we built a 3-bit binary up counter with asynchronous reset low. Okay, this is what we built. So make sure that you have all these commands. Okay, you want to go by notepad or the code or the command. Okay, yeah, I have the commands Windows up. So make sure that you type in the commands I show you on the screen and then execute your simulation and then get the binary count sequence. Okay. Okay, today we just built a 3-bit binary up counter with asynchronous reset low. Okay, so let's continue. Are we all set with the simulation? Mhm. Pay extra attention to the window. Look at this name. You see the dot dot dot? That means the name is very long. It cannot show everything. Okay. So what you want to do is you want to move this boundary to the right to extend the window such that you can see everything. Okay. All right. Any questions so far? When you say it doesn't work, is your code not working in VHDL or your commands not working such that your waveform is different? Well, before you put in the code, you need to start your simulation. When you start the Modelsim, default is not in simulation mode. You need to go to simulate, start simulation, and then they ask you, hey, what you want to simulate? Then you pick design 0. Then you can simulate. Then you can type in the commands. If you just type in the commands, it's not going to work because you have not started a simulation yet. Well, if you can give me your code, sorry, the passcode, I can remote into your machine and take a look. Yeah, so if you need me to support you right now, please give me the passcode so I can get into your screen and tell you what's going on. So please send me the passcode. Okay. All right. So right now I'm helping Manny. The rest of you, please make sure that you can get the simulation waveform, okay, like this. Yes, Manny, I'm trying to get into machine, but it's extremely slow. Oh, he doesn't even. He says your machine is offline. Let me try it again. No, it's not letting me through. Okay. Okay. Yeah, I can see your screen. Let me see if I can click on anything. Oh, no. Okay. So go to the terminal of Modelsim. Restart your simulation. Restart. Yes, that's correct. Yeah. Okay. And then type in those commands or copy and paste those commands. You can do everything at once. Yeah, it works. Okay. We're all set. Okay. All right. So Manny also is all set. Let's continue. All right. So any question about the counting sequence? And any question about the code, the VHDL code that we use to create this counter? Yes, very likely you just want to restart your simulation and then you will just work fine. Okay. Okay, Doc, what's the problem with you? So send me the code. I can get into your machine. Yes, if you need me to look at your screen, please send me the passcode so I can see your screen. Yes, Doug, if you need me to help you, you need to send me the code. Okay, so to those who already finished, we can get out from this too. Then we'll talk about next topic. Okay, so file, exit, quit, and then quit. Okay. Okay, so Doug, you need to look at your code. Your code has syntax error. Okay, so let's go to the first error message. Okay. Yeah, scroll to the first error message. Let me see if I can control anything. All right, so let me drive. No, I cannot click on your screen. Scroll to the top of the message window. I want to see the first error. This is not the first. There must be more before that. Scroll up. Okay, so it says line number 12. Yeah, you have a extra semicolon at the end of line number 11. There shouldn't be any semicolon at the end of line number 11. Right, let's save everything. We compile the project. Yeah, you need to file save project. Okay, line number 12 again. Scroll up, please. Scroll up more. Yeah, you must be missing a semicolon somewhere. Now let me see. I can click on your window. You need to let me to click on your screen. Otherwise, I cannot help you. You disable that. So I cannot click on your screen. I only watch what you're doing. I cannot do it for you. Now just look at my screen. Make sure that you match everything. Word for word, space for space, symbol for symbol. Okay. I don't know because I'm not on your screen. I cannot see your setting. But right now, if you look at this, I cannot click on your window. I can only watch. Okay. Yeah, the spacing doesn't matter. If you want to Google it to figure out how I can click on your window, but right now you can see that clearly. I cannot do it. So I can only maybe edit. No, I you can do that afterward. But right now you can see that I cannot do anything. I can only watch what you're doing. Yeah. It's okay. I'll post the code after class and then you can use it. Okay. I want to terminate. All right, let's continue. All right. Sorry about the wait. So next, we're not going to type in a new design. We're going to talk about the topics we need to talk about today for D3. Now, today, if you look at this circuit, it's a counter, okay? But sometimes you want to work on circuits where the counter doesn't go to any output. The counter is internal, okay? Yeah. When you work on those kind of circuits, you need to do something special, okay? So I'm giving you one example here. All right. Suppose we do this. We have designed an internal counter, and I just give a name. So this is my internal counter. The counter counts from 0 to 1 to 2 to 3 to 4, and then goes to whatever. Okay, just keep counting up. Okay, all right. And then I call this my counter. I don't really care about how many bits we have. It could be 10, it could be 20, it could be 30 bits. Okay, all right. Then I can develop a circuit which has outputs. There's a function of the counter, or the output depends on the count. Okay, all right. So this kind of circuits, the counter will be internal for sure because you don't need to know the counter at the output. What you care is the output that depends on the counter. Okay, output depends on the counter. All right. So that one looks something like this. So I'm going to give you another example here. So output depends on the counter. So I still have my counter, which still counts from 0 to 1 to 2 to 3 to whatever. But my counter right now changes value to 1 every time he sees 2, 3, 4, 1, 2, 2, 3, 4, 12, 13, 14, 22, 23, 24. And this process repeats. And then I just call my output Q. It could be P, it could be Q, it could be R, it could be S. It doesn't matter what the name is. It's just an output. Okay? All right? So far, any question about the presentation, about the counting sequence, and then the output that depends on the counter? No question? Okay, let's continue. So we have internal counter, output based on internal counter. So here are the questions. What is the input clock frequency? Anybody? On DE10 light, it is 50 megahertz. What is a clock period? 20 nanoseconds. Okay, now if you change your board, these numbers will change. Okay, it could be 50, it could be 100, it could be 20, it could be 10, it could be whatever. Okay, all right. So, why does this matter? If you're going to calculate the output time, you need this information. Because if you look at this, 0 to 9, there are 10 clock cycles. Out of these 10 clock cycles, only 3 clock cycles output 1. So that means it's 3 over 10. Another 3 over 10. Another 3 over 10. So that means Q is equal to 30% of 10 counts at 20 nanoseconds per count, right? So that means this is 30% of 20 nanoseconds times 10 equals to 30% times 200 nanoseconds. Understand? So this is equal to 6 nanoseconds, 60 nanoseconds. Okay? So the Q will go to 1 for 60 nanoseconds. Okay? And the frequency of it is going to be what? It's not going to be 60 nanoseconds, 1 over 60 nanoseconds. The frequency of it is from here to here, or from here to here, which is 10 clock cycles. So the frequency is 10 times smaller than the input frequency. I said 10 times smaller. Sorry about the typing. 10 times smaller. This is going to be 50 divided by 10, 5 megahertz. Okay? Okay. So if you're going to measure the frequency for the output Q using a scope, it's going to be 5 megahertz. Why? Because every 10 cycles, the output changes value. And then every time the output changes value, the output will stay high for 3 clock cycles, which is 60 nanoseconds. All right. But if you look at this carefully, you can see that. So what's the big deal here? Well, the big deal is initially the counters go from 0 to 1 to 2 to 3 to 4 to 5, and then keep going up to 20 to 30 to 40, 50. But you look at this carefully, your counter doesn't have to go up to 10 at all. Why? Because your output changes every 10 clock cycles. Your output doesn't change every 20. Your output changes twice in 20 clock cycles. So that means we don't have to make the counter go up to 20, 30, 40, or 50. We only need to make it going up to 10. So this is the improved output based on the improved internal counter. So if you look at this, it says the counter will go from 0 to 1 to 2 to 3 to 4 to 5 and go to 9, and then go back to 0 and then 1, then 2, then 3, then 4, then 5, then 6, 7, 8, 9. And then repeat this process. And then if you measure from here to here, this is 10 cycles. From here to here, this is another 10 cycles. Okay? So this number 4 behaves exactly the same as number 3. Okay? This is 50 megahertz, 20 nanosecond per count. Output frequency is 5 megahertz. The period is going to be 1 over 5, 200 nanoseconds. So within this 200 nanoseconds, only 60 nanoseconds is equal to 1. And then the remaining 140 nanoseconds, output is equal to 0. Okay? Any questions about this? Any question about 1, 2, 3, 4? Okay. All right. So what's the big deal? The big deal is the counter itself is a process. Look at our code. This is what we had. The Q in our example does not have its own process. But for this particular design, this has to be in another process. So you have two processes running in parallel. One is dedicated for the counter. The other one is dedicated for the queue. Understand? You cannot simply connect the counter to the queue because the queue is 1 bit output, but the counter itself is 3 bits. Understand? So how does this thing relate to us? So let's look at assignment number 3, D3. So for D3, you're going to design circuits that will work with a clock. Okay. So in this case, I ask you to use clock 2, max 10, clock 2, 50. Okay. And I'm going to ask you to use GPIO1.35 as output. Okay. Now, since we don't have scope or oscilloscope at home, you need to run simulation of this. Okay. So the input clock based on the manual is 50 megahertz. Okay. The output of your circuits is going to create the outputs at a different frequency, okay, and different duty cycle. Okay. So what is a duty cycle? A duty cycle is Q. You look at this, Q is 30% of the output. That means the duty cycle is 30%. A square wave is 50-50, meaning that 50 high, 50 low. So a square wave is 50% duty cycle. But any digital signal, can has a frequency and a duty cycle. In this particular case, is going to be 30% duty cycle. Okay? So for you, I will give you, hey, what is the period of the signal and what is the duty cycle? So based on those two numbers, you need to figure out first, how many counts do you need? Because the more counts you have, the slower the frequency. Next, based on this count, how many clock cycles does Q need to be high to make that duty cycle? Okay, so for example, if the count is equal to 100, which is 100 counts from 0 to 99, and your Q is equal to 40 counts, that means your duty cycle equal to 40%. Understand? So on Ulearn, I will post the X and Y for each student, and each student will have a different value. Okay? And then when you run simulations, you should see that your counter will work, and then your output will change at the right time, and the generated frequency can be simulated. Okay? All right. So what do you need to turn in? Same thing. Archive project, command file, and the BMP waveform. Okay? So these are the three things. Because I don't believe you have a scope probe or oscilloscope at home. Okay? If you do, please use it. If you don't, that's fine. Just use simulation. Okay? I don't have an oscilloscope at home. Okay? So I cannot show you live how it works. Okay? So any question about D3, which is due next week? Okay? If you really want to get a scope at home, there are some low-cost digital scopes. Okay? Yeah, if you go online, you can find them. They are very cheap. They're USB based. They're good for a couple, like a few megahertz, and they're very handy. You just need to buy the thing, and then they give you the software for free. Yes, I'll post the lecture after class. Okay. All right. So if you don't have any questions, you can leave the live. And some of you, let me see, not some of you, only Doug has a problem with his setup. So I'm going to support him. And the rest of you, you can terminate the live. And I'm going to terminate the live later when I finish with that. Okay? All right, Doug, please send me the code. I'll log into the machine, and then make sure that you can let me click on your screen. Otherwise, I can only watch you what you're doing. I cannot help you that way. Yes, Aaron, you're all set. Okay, let's open up project number D1. So, Doc, please open project D1. Okay, and then you just compile the project, please. Yeah, plug in your board to your virtual machine and then click on Programmer. Okay. So right now, what we'll do is we click start. Okay. So let's do this. Click on auto detect. No, you don't want to do that. Well, if you that's broken, very easy. First you click on no, and then you delete the file, and then add the file again. But I don't think so because D1 is very simple. So what you need to do right now is click no and click auto detect. Let's see what happens when you click auto detect. No, something is wrong with your board or your cable. I would recommend to try a different cable. Try a different shorter cable, and then redo this because it is not even seeing your device. That's what it means. Remember, when you stretch it, you're stretching the cable, but you could be internally broken. Okay. Yeah, this is the problem. The problem is he's not seeing the board or the device. Yeah. So I will try a different shorter cable. So if you want to get a cable, make sure that it's shorter, not like long. So maximum length is I think is 3 feet, but I've seen people using 1 foot or 2 feet or 1.5. That's okay too. Yeah. So you definitely you no, you don't want that. Yeah, your USB blaster is being recognized. That's no question. Otherwise, you don't even show up. Okay. Okay. Yeah, I think you should try a new cable first before we start going crazy on this. Okay. For D3, you don't need a board. You just need to run a simulation. You only need it for D2. Um. Yeah. If we have to, I can give you a loaner board. I can go to the school, get one, and then give you. Yeah. I know it was working. You mean these boards are pretty good in quality. I haven't seen, well, for the last 4 years, I've seen one broken uh, out of probably 50 of them. One broken, and then it wasn't even the USB blaster. It was something else broken. Yeah, the cable doesn't have to be expensive. These are very generic USB cable, short. There's no need to get it from Amazon. You can just walk into like any store. For example, if you go to Best Buy, you go to Walmart, they have these everywhere. These are very, very generic USB cable. But remember, do not do not use the long one. Use the shorter one. Yeah, you try a printer first. If that works, great. Yeah. Okay. Anybody else need support? Okay. If nobody needs support, I'm going to terminate live in 1 minute, and then I need to get ready for next class. Yes, you need to display all the hex digits on hex one. That's correct.